Hey everybody, welcome back to a Robinson Rant. And yeah, let's keep going. I would be remiss if I didn't add this extra lecture in because with this tiny lecture or two's worth of information, you can really broaden the scope of your analysis techniques. And so even though we're nearing the end of the course, it's still good to cover this. So we're going to actually combine a couple of ideas and I'll walk you through. But right now, where we stand, we have introduced these ideas of the complex plane and using Euler's relation to get the impedances of circuits. In other words, we start off with something like a function, a potential that is being applied to our circuit. We add in an imaginary component to make the expression of this function a little bit easier by applying Euler's relation. So we end up with something like this. Now, the fact that we have introduced the imaginary axis in our complex plane and Euler's relation allows us to now model our circuit components as all being some sort of impedance. Now that impedance can be real, it can be imaginary, but that allows us to simplify our analysis technique. In other words, rather than worrying about differential equations, we can now just simply worry about linear equations. So that helps us out. Now, the thing that has been unsaid so far is that up until this point, we have been working with a constant omega. Or if you prefer, we have simply chosen a value for omega and then run the entire analysis. The question then becomes, well, what happens if we have multiple omegas? There's nothing that says it has to just be a single term. And you probably already know what the answer is here. Okay? Yeah, you've got it. So let's go ahead. What happens if omega t is something like cosine of omega t plus cosine of 2 omega t? In other words, I am adding two cosines, one that has twice the frequency of the other. How would this affect our analysis? And just for convenience, let's go ahead and consider something like an RLC circuit in series, just so that we have some sort of concrete example that we can apply this to. You ready for it? Okay. So, well, what we would do, let's go ahead, we'll add in the imaginary component to our expression. So what I mean by that is we'll add in a cosine of omega t plus a j sine of omega t. Okay? And we'll do the same thing for the second term, the cosine of 2 omega t plus j sine of 2 omega t. Okay? And then by applying Euler's relation, we end up with this expression, which we could have probably jumped to immediately. Good so far? Okay, now say we're interested in the current flowing through this circuit. And so now that I have transformed this into the complex plane, the frequency domain, okay, I can now write my three elements, R, L, and C, in terms of their respective impedances. And so my equivalent impedance can simply be written as the impedance of the resistor, R, plus the impedance of the inductor, J omega L, plus the impedance of the capacitor. We have a negative J omega c. And here I need to be careful. Notice that I have omega occurring in my expressions. What does this mean? Well, if I have different omegas, my impedance changes. In other words, the impedance is a function of the frequency. So for clarity's sake right now, I'll go ahead and I'll put omega n in here. Good so far? Okay. So we have our equivalent impedance could be written as R plus J omega L minus 1 over omega C. And I'll put again that subscript in there just because we're dealing with two different frequencies, if you will. Well, let's keep going. We now know we have V of t is equal to the equivalent impedance times I of t. And so we have V of t, that is written as e to the j omega t plus e to the, I'll put 2j omega t equals, we have our equivalent impedance, R plus j omega nl minus 1 over omega nc. That's I of t. Now I'm going to go ahead and go through and multiply by the complex conjugate. And so we end up with something like R minus J omega NL minus 1 over omega NC equals R squared plus omega NL minus 1 over omega NC squared I of t. And so what we end up at the end of the day, we have something like, oh, excuse me, you should yell at me. I forgot that e to the j stuff. E to the j omega t plus e to the 2j omega t. Now I've buggered it all up. I've run out of space. There we go. And so what do we have at the end of the day? Go ahead and go to a new page. We have that the current as a function of time is equal to, we have an R minus J omega N L minus 1 over omega NC divided by the quantity R squared plus omega NL minus 1 over omega NC squared e to the j omega t plus e to the j 2j omega t. Pretty cool, right? Now let's look at this for a second. We notice that because I have a linear combination of two cosine functions, you could think of I of t as being two pieces, right? You have a piece due to the cosine of omega t and a second piece due to the 2 omega or cosine of 2 omega t. You've probably already seen this, right? This should remind you of that principle of superposition that we talked about earlier in chapter 3. In other words, the total current, I total, can be thought of as being the contributions due to the individual sources. Now we can think of this as being broken up into two pieces. The first one being r minus j omega L minus 1 over omega C divided by r squared plus omega L minus 1 over omega C squared. And notice I've dropped that subscript n, e to the j omega t. There's my source 1 contribution. Added to that, of course, would be my source 2 contribution, the exact same expression, except now instead of omega, I have 2 omega. Right? Remember that that has twice the frequency. So anywhere where I saw omega n, I need to put in 2 omega. And like I said, because the impedance is frequency dependent, we will see that the resulting current through this RLC circuit has different amplitudes for different sources. It's kind of cool. Now, of course, if you want to get back out of the frequency domain, we'll have to unpack this. So for example, you'd have I total equals, well, let's reintroduce Euler's relation here and then throw out the imaginary pieces. So you'd have something like r cosine of omega t plus omega L minus 1 over omega C sine of omega t over r squared plus omega L minus 1 over omega C squared. And similarly for the second piece, with the substitution that instead of omega, you'll write in 2 omega. Pretty cool, huh? And so not only have you determined, you now have the technique for analyzing an AC source, you have the ability to do combinations, right? Linear combinations. Cool, huh? Here, let's get an idea of what this looks like. Okay? Notice a couple of other interesting things. Now, I'll focus in on just one term for a moment, say this first term, okay? Just for sake of clarity. You can imagine, for example, what happens to the total current, this term, let's say this first term, what happens to this first term in the limit that omega goes to 0? Yeah, you see it? Well, if we look at the denominator, we notice that the denominator goes to infinity. Okay. How about the numerator? Well, this first piece on the numerator goes to, 1, right? Cosine goes to 0, or cosine of 0 is 1. So this first piece goes to some constant value, r. How about the second piece? What happens to the second piece? Yeah, hopefully you see that second piece goes to 0. Okay. If you don't see it, you can apply L'Hopital's rule, right? The limit as omega goes to 0 of sine of omega t divided by omega c, right? That's really what we're worried about here. Okay. Well, that if I plug in, I get 0 over 0, an undefined thing. So then I can apply L'Hopital's rule. L'Hopital's rule. I think there's a circumflex over the O. And what that is, you take the derivative of the top, omega cosine of omega t. You take the derivative of the bottom, and then you perform the limit. And here we see that in the limit, it's no longer undefined. It's not 0 over 0, but rather it's simply 0 over some constant, which equals 0. This tells us that the term we were considering tends to 0 in the limit. So what do we get here? We get some constant value plus 0 divided by infinity. And so our final answer is 0. Right? At really low frequencies, this term is 0. Well, how about at high frequencies? Let's go ahead. What happens in the limit as omega gets really large? Yeah, hopefully you got it. The first term in the numerator, regardless of how large omega is, that first term is always limited, right? It's either positive r, it's between positive r and negative r, so it's some finite value. Okay. How about this second term? Well, sine remains some finite value. This second term in the parentheses goes to 0, and the first term goes to infinity. So the numerator, what we have is something like infinity. We have omega, excuse me, frog in my throat. You essentially end up with an omega L sine of omega t. Well, how about the denominator? Well, the r squared is minuscule compared to infinity. This 1 over omega c goes to 0, and so you end up with omega L squared. And so you see again that you tend to 0. So if too small of an omega, you're at 0. And that should make some sense. If the current is not oscillating quickly, the capacitor fully charges and the current should be 0. Conversely, if it's oscillating too quickly, high omega, the inductor says, whoa, 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 I don't like these changes, and should also prevent the current from flowing. Pretty cool, right? Well, how about the phase? Oh, let's take a look at that real fast. Okay. So what I've prepared for you here is a graph on Desmos, and you notice that I have my current programmed in, r cosine of omega x plus rigmarole times the sine. Okay. So that's represented by this red line here. And then I've also programmed in the black line. That would be my applied potential of the source. Okay. And notice I've programmed them both in terms of variables omega, so we'll play around with what omega does. Let me go ahead and I will, I'm not happy with this axis, so let's go ahead and I'll put in 1.5 and I'll put in 1.5. Hopefully that'll help us out. And you notice that if I put in 0, nothing, boring, but I'll put in a really small value, 1/10 of a radian per second. And you'll notice the amplitude of the red line is rather small. And in fact, if I could go further, let's say I go 0.01. Okay, let's see if I can make it even smaller. Okay. You'll notice that, maybe I make this 1. You'll notice that even smaller, that amplitude of the red line is really small. In other words, as omega tends to 0, right, the resulting current is very small, the amplitude. Okay. Well, what happens if I start jacking up omega? As I start getting larger on omega, you'll notice, first of all, that more waves are present on the screen. It's because I'm causing the oscillation to go faster. And in addition to that, the amplitude of the resulting current across my circuit is increasing. And you'll see, as I get closer and closer, you see it's almost 1, right? Right there, when omega is equal to 1, they actually match. Well, what happens if I go further than that? Let's go to 10, and I'll increase the step size here. And well, let's go ahead. what happens? Ah, yeah, you see that? You see that? As I increase, the amplitude increases, and it matches at omega is equal to 1. Then what happens past that? As I further increase the amplitude, or the frequency, you notice that the amplitude begins now to decrease. It's a bit harder to look at just because I have so many cycles on the screen. Okay. So let's go ahead and I'll just decrease the range, the window range. But as I increase omega, you notice that the amplitude keeps getting smaller again. So there's some peak amplitude. Apparently for this, it's at 1 radian per second. And then decreases again. Pretty cool, huh? So we have an idea about how omega affects the amplitude of the contributions, if you will. And so for this specific case, where RL and C are all equal to 1, the e to the j omega t, we'll say it's 100%. And the e to the 2j omega t, the amplitude is 55%. But wait, there's more. So that takes care of the amplitude piece. And I'm sure you already noticed the other issue, the other interesting piece, is the phase angle, right? Theta. And if we go back and look, you know that the phase angle is given by the arctangent of the imaginary component divided by the real component. Well, the imaginary component was omega L minus 1 over omega C. And the real component was given by R. So let's go ahead. Let's take a look at what happens to the phase, the relative shift between the applied potential and the resulting current as the limit as omega goes to 0. What does that give me up here? Well, I get tangent -1. That first term goes to 0. The second term goes to infinity. Oops, excuse me, I had a negative sign here. There's a negative sign in front of that imaginary term. So omega L goes to 0. I have -0 minus essentially infinity over R. So I get something like the inverse tangent of infinity, positive, which is equal to, not undefined. Good, yeah. This is pi over 2. So in other words, at low frequencies, I expect my current to be out of phase with my applied potential by pi over 2. Okay. Well, what happens in the limit as omega approaches infinity? Well, again, you see that now what happens? Well, rather than that first term in the numerator being 0, that first term is infinity, and the second term is 0. And what do I get? Yeah, the tangent of negative infinity, which is negative pi over 2. So what do we expect to see? We should see it starting out pi over 2 out of phase with the applied potential. As we increase omega, it will at some point, we already saw it, but at some point be completely in phase, perfectly in phase. And then as we continue, it will shift out of phase again. Okay. From pi over 2 out of phase to negative pi over 2 out of phase. And we saw that already. Let's pull up the Desmos again. If we start off really small, the Desmos, let's pull up Desmos again. And let me go ahead and I'll take this out to 100, just so we can see several cycles. Now, we actually have to run the numbers to confirm this is pi over 2 out of phase if you wanted to do it numerically. What I'll say is that, look at this. We see that when the black line is 0, the red line is at a maximum. Okay. So we know that it's shifted by pi over 2. Now, what happens if we continue and you see that as we increase, first of all, the amplitude goes up, but now all of a sudden those two lines are on top of each other. Right? What does that mean? While one is peaking, the other one is also peaking. They are completely in phase. And then we can keep going, and as we increase again, we notice it gets shifted to the right now, further and further out of phase, until finally you can now see that when the potential is 0, our current is at a maximum. And so now it's shifted pi over 2 degree, or pi over 2 radians out of phase again. What we're really witnessing here is the individual contributions of the capacitor and the inductor to the resulting current. When the contribution of the capacitor perfectly cancels that of the inductor, we notice that it's in phase. The current and the potential are in phase. Or alternatively stated, the impedance is only real, or we call that a purely resistive circuit. The contribution of the capacitor and the inductor perfectly cancel. And when I say contribution, I should say the contribution to the imaginary component. Okay. So again, we see that we can see not only an amplitude variation, but also a variation in the phase, how far shifted the resulting current is from the applied potential. Now, another graph to see this would be this guy. So let me walk you through again. What I've plotted here is the inverse tangent. Okay. Now, unfortunately, because of how Desmos works, I had to use x to represent omega. So your horizontal axis here is the applied frequency of the source. And the y-axis is the phase shift of the current. So horizontal axis, frequency of the source. Vertical axis is the phase shift. And you notice, again, at 0, we're at a phase of pi over 2. And as we increase our frequency, you notice that the phase becomes lower, smaller, and smaller, and smaller until exactly at 1. And this is because C and L are both equal to 1. But at 1, at a frequency of 1, you'll notice that the phase shift is 0. And then as we continue increasing the frequency, the phase shift will continually asymptotically approach pi over 2. Excuse me, negative pi over 2. So this is a different way of seeing that information that we visually saw on the previous graph, comparing the two shifts. Now, of course, if you want, you can play around, you can fiddle with changing the capacitor value, changing the inductor value, okay? Changing the resistor value. You notice that resistor value doesn't change the location where the in phase occurs, whereas changing the capacitor value or the inductor value does. Pretty cool, huh? Okay. So that being a brief foray into, hey, we can use that principle of superposition to consider the individual contributions to total current. Of course, I said total current, but you could replace total current through the circuit with potential drops. Right? Because the potential drop across our circuit elements is proportional to the current, then once you have the current flowing through the circuit, you can say something about the potential drops. Okay? And now you have a larger breadth of things that you can cover. Not only does it have to be a sine or pure cosine or a pure sine, it can be a linear combination of cosines or sines. Now that's the jumping off point for our next idea. Okay, so I'll save that for the next lecture video, but that is the jump off point to something called Fourier analysis. Okay. So I'll introduce a mathematical, I'll say convenience. Okay, and what we'll find is that we can express any repeating function as a linear combination of sines and cosines. And once we have our linear combination of sines and cosines, we know that we can use this idea of superposition to analyze the full circuit. Pretty cool, huh? Okay, so I'll say stay tuned for that, and we'll catch it on the next lecture video. I thank you for your attention. I'll see you next time.